All right, thanks Dave for the introduction. Let's go ahead and get started now. So image enhancing processes and filters require good estimates of the reflection slopes in seismic images. One such process you'll see just after the break today, presented by Jinming Wu, where he estimates the seismic normal vectors to extract horizons automatically. Tomorrow he'll also present on using the same method, estimating seismic normal vectors to better detect unconformities in seismic images. And I'll show later in my presentation today how estimating these seismic normal vectors is equivalent to estimating the slopes in the seismic image. The two main methods that I'll be focusing on today, the main methods used in industry, are the plane wave destruction filter method and the structure tensor method, both of which I'll give a quick overview now. So let's start with the plane wave destruction filter. Sergei Fomel described in his 2002 paper, Applications of Plane Wave Destruction Filters, a way to estimate slopes using plane wave destruction filters. Not only does he describe the theory in his paper, but he's also implemented this process in the Madagascar software package, and it's called SFDIP is the method. So what exactly is described in this paper that he's written in 2002? Well, the plane wave destruction filter can best be described as a prediction error filter, where we start with a single sample on a single trace and attempt to find the slope that best estimates the sample in the adjacent trace such that the filter output is close to zero. But the nature of this process could give us a slope image with highly varying slope values and thus giving us no insight. And for that reason, we have the regularization term on the right described by epsilon, the scalar coefficient, d, the gradient operator, and delta p, the change in slope. And this just says that we want to smooth the derivatives of the changes in slope. So next we have the structure tensor method. And in last year's CWP meeting, Dave gave a great presentation, very finely detailing what the structure tensor is, and so for that reason I will not do that. But I will describe how we can use structure tensors to estimate slopes in a seismic image. So for a 2D image, we have a 2x2 symmetric tensor matrix. And once we have this tensor, we can do an eigendecomposition, the equation that you see above, to get eigenvectors u and v. And we can do minus the second component of the eigenvector over the first component of the eigenvector to get the slope. Now v represents the eigenvectors parallel to seismic features in an image, and u represents the eigenvector normal to the seismic features in the seismic image. And so in Jinming Wu's presentation, you'll see them described as seismic normal vectors. Okay, so now that we know what these two methods are, how can we begin to get a good idea of the accuracy of these two methods? Well, it starts with a synthetic image with structural complexities that may represent complexities that we may see in real seismic images. And I'd like to point out a couple of these features here today. So very easy to see is this unconformity here, but an unconformity that may not be so easy to see is one in the shallower portion of the image. We also have a couple faults, one intersecting the other, noted by the broken red line sloping to the right of the image. And as we go from the upper left-hand corner of the image to the lower right-hand corner of the image, we're seeing increased slope values. So we have this synthetic seismic image, but in the real world, we're likely going to experience noise. And for that reason, we also compute two additional synthetic images with increased RMS noise to RMS signal ratio. From here on out denoted as noise to signal ratio. So we have a noise to signal ratio here equal to 1/2. And so some of the structures are getting a little bit more difficult to see. And for noise to signal ratio equal to 1, where we can really only pick out strong reflectors in the image. But the cool thing about having a synthetic image is that we know the slope values exactly for every sample in the entire image. And that's this image that you see here. Now quickly I'd like to note the shallower portion of the region. It all looks green and like the same value. But if I change the color scale on the right, oh, okay. Well, something happened with my slides, but you'll notice that there it is. Okay, that above the unconformity we have constant 0 values, and just below it we have constant, very shallow, non-zero sloping values. And so I'd just like for you to keep that in mind as I continue on in my presentation. So if you remember the regularization term I showed earlier describing the plane wave destruction filter, you'll remember that there was an epsilon term. But if you look in the software, you're not going to see an epsilon term. Instead, you're going to see parameters rect1 and rect2, which describe the horizontal and vertical smoothing of the smoothing aspect of estimating slopes using plane wave destruction filters. Now the reason why I point out this rect1 and rect2 parameters is because we need to find analogous parameters between these two methods to best test them against one another, such that we don't give one method an advantage over the other. And those analogous parameters are sigma 1 and sigma 2 in the structure tensor method. So a good, quick one number value that can give us an idea of the accuracy of each method is to compute the RMS error, where p tilde is the estimated slope and p is the known slope value. Again, this is going to give us one value for the accuracy for the entire image, estimating the slopes. And we can actually use this calculation, this RMS error calculation, to produce this image where we have different combinations of rect1 and rect2. Now, the reason why we compute this test is so that we can find the optimal rect1 and optimal rect2 values for the rest of our tests, so that we, like I said earlier, don't give one method an advantage over the other. And for the plane wave destruction filter method, the optimal rect1 value is 76, highlighted by the white oval, and rect2 value is equal to 6. I'd also like to note that I computed this image for a noise to signal ratio equal to 1/2. Similarly, I compute the same image for sigma 1 and sigma 2, but also highlighted by the white oval, we see that the optimal parameters are different. Sigma 1 being 24 and sigma 2 being 1. I'm going to stay on these two images a little bit longer because it's very important to understand why we computed this test and why I'm trying to point out which values of sigma and rect that we chose for the test that I'll show you later. So again, I'll reiterate, we wanted to choose the sigma and rect values that are optimal for each method. The sigma and rect values that give us the lowest RMS error value. So there's some trade-offs here. So as you can see, for different combinations of sigma 1 and sigma 2, the structure tensor method is a little bit more sensitive to these different combinations, whereas the plane wave destruction filter is not. That being said, if you look at the lowest value that we can achieve for the plane wave destruction filter for RMS error, it's about 0.66, whereas for the structure tensor method, it's about 0.4. Okay, so for the tests that I'm going to show you later on today, these are the optimal values. These are the values that I use for the rest of the images computed today. So again, I'd like to remind you what the images look like for noise to signal ratio equal to 0, noise to signal ratio equal to 1/2, and a noise to signal ratio equal to 1. The reason why I'm showing you these is because for all of these images and for noise to signal ratios in between these different values, I've computed an RMS error curve as a function of different noise to signal ratios. And what you'll notice right away is that for the plane wave destruction filter, for every noise to signal ratio we have a higher RMS error value. And to better understand why that is, perhaps we should take a look at what the estimated slope images are for both methods. So starting with a noise to signal ratio equal to 0, we get the following estimated slope images. For the plane wave destruction filter here, and for the structure tensor method here. And something I like to point out quickly, flipping back and forth between the two, is that the structure tensor method estimates higher slope values, which are closer to the correct values than does the structure tensor method. So plane wave destruction filter, structure tensor method. Another thing to note is that both methods are smoothing across the fault, and that's because of this smoothing aspect of both methods. Here for the structure tensor method. And they are also both smoothing across the unconformity highlighted by the black oval here. We're actually seeing more smoothing for the plane wave destruction filter because, if you recall, our optimal rect 1 value was 76, which is significantly larger than our sigma 1 value, optimal sigma 1 value, which was 24. Okay, so now, and I'll remind you what the known slope values are, and you'll note that we have sharp discontinuities across the fault and at the unconformity. So now let's compute the same images for noise to signal ratio equal to 1/2. And what you'll notice right away is that for the plane wave destruction filter, we're estimating much lower slope values, as is for the structure tensor method, but in more areas than for the plane wave destruction filter, we're able to estimate higher slope values. Again, here are the known slope values. And for a noise to signal ratio equal to 1, the plane wave destruction filter method is really not estimating very high slopes at all, as is the structure tensor method, but again, in some areas we're able to estimate these higher, closer to the correct slope values. So something that hopefully is troubling you, and I know it troubled us, was why are two of the most commonly used methods for estimating slopes, why is one struggling a little more than the other? It couldn't be that the implementation was incorrect because I used the exact implementation that Sergei Fomel implemented himself. I used the method in Madagascar. So perhaps it was something else that has to do with the method. And the nature of estimating slopes using the plane wave destruction filter is that it is itself an iterative method. So it requires initial slope values and a number of iterations to hopefully converge to what the correct slope value is. So what we decided to do, again, the known slope values. So what we decided to do was up the number of iterations first. So for all the images that you saw earlier today, I used the default number of iterations, which is equal to 5. So why not exaggerate the number of iterations to 100 and see what our results would be. And as you can see, we get slightly better slope values. So 5 iterations, 100 iterations. But maybe not enough to justify a jump to 20 times the number of iterations. Because again, increasing the number of iterations 20 times also greatly increases the computing time required. And for a noise to signal ratio equal to 1, there's really not much difference at all. 5 iterations, 100 iterations. So maybe we should actually check to give it different initial slope values. So the default for the plane wave destruction filter is to give it initial slope values equal to 0, which is generally a good assumption because the nature of seismic images is that we're mostly going to have horizontal features in the image. So maybe it's not a bad idea. But if you'll recall, in our synthetic image, on the lower right-hand portion of the image, we have high sloping values. So if we're starting at 0, it may take longer, it may be more difficult to converge to the correct value for such high sloping values. So why don't we give it better initial slope estimates? In fact, why don't we give it the best initial slope values that it can possibly get, which is the correct known slope values. And that's what we did. So here, you'll actually notice, and if I flip back to the 0 initial slope value, is that we see some improvements on the right-hand portion of the image, but the main improvement that we see is a discontinuity at the fault and unconformity. Well, why is that? If the rest of the image is being smoothed, as you can see here, 0 initial slope values and known slope values, why are we seeing this discontinuity at the unconformity and the fault? Well, that can be described by the equations that describe the plane wave destruction filter for estimating slopes. The regularization term on the right, again, smooths the derivative of the changes in slope, which preserves the discontinuities at the unconformity and at the faults. So now that we saw how, applying the initial slope values equal to the known slopes for a noise signal ratio equal to 1/2, we can take a look at, so now we have applied separately, increasing the number of iterations and providing initial slope values equal to the known slope. Why don't we combine the two and see what results we get? So for 100 iterations and known slope values, we see the image that you see here. And so if I flip back and forth between the initial slope value equal to 0 and equal to the known slopes, again, the only main difference that you see is the discontinuities at the unconformity and at the fault. Okay, so for all the images that I showed you, again, we had noise in some of our different synthetic images. But it may be that the method for estimating slope was having difficulty in a certain area that was especially noisy in that image. And so for that reason, we calculated the sample mean for 100 different synthetic images, all with a noise-to-signal ratio equal to 1/2, but with different realizations of noise. And we get the following images. For the plane wave destruction filter, and we get more continuous estimates of slope, and for the structure tensor method. But, and as you may have noticed, we are seeing higher estimated slope values for the structure tensor than for the plane wave destruction filter method. And again, this is computed for a noise-to-signal ratio equal to 1/2. I'd like to recall the RMS error curve and note again how for every noise-to-signal ratio, the plane wave destruction filter is producing higher RMS error values than does the structure tensor method. Maybe it's because in one spot in the image where we have a very erroneous value that's causing the entire image to have a higher error value. So the way we can test that is to look exactly where our errors are occurring by computing the sample standard deviation, where tilde p, again, is the estimated slopes, and p is the known slopes rather than the sample mean, because we want to know what the standard deviation is against the known slope values. And we get the images that you see here. So one thing that we'll notice, and that you probably guess, is that we have most of our errors across the unconformity, across the faults, and where we have rapidly varying, highly sloping values. Now the reason why I chose my color scale to be the way it is here is because if you'll notice in the upper portion of the images, we're also seeing errors at the unconformity where it should be fairly easy to estimate slopes because they're constant values. And here's for the structure tensor method. And if I flip back to the plane wave destruction filter structure tensor method, you'll notice that for every sample in the image, we're seeing higher standard deviations for the plane wave destruction filter than for the structure tensor method. And this tells us that we're not seeing just one very high erroneous value that's causing the error for the entire image to be higher in the plane wave destruction filter than for the structure tensor method. Oh, since we have an image of standard deviations and we have an image of known slope values, that means for every sample in the image we have two values, a slope and a standard deviation, meaning that we can plot these two against each other and see how the standard deviation behaves as a function of slope. And as you can see here, as slope increases, we see a fairly linear trend of higher standard deviation values. And for the structure tensor method, something very similar, but with shallower linear trends than for the plane wave destruction filter method. I've shown you today the two most commonly used methods for estimating slopes in seismic images and where they may struggle a bit, and that again is across unconformities and faults due to the smoothing nature of both methods and where we have rapidly varying, highly sloping values. Now the research that I've done and that I've shown you today is kind of a machine for testing the accuracy of these different methods in estimating slopes. But the end result and the hopes for future research is to use a third method to plug into this machine using dynamic warping to estimate the slopes in seismic images. So with that, I'd like to thank the CWP faculty, staff, and colleagues, and friends and family, and I'd be happy to take questions. Thank you.